Yeah, so let us come to strain displacement relation. Okay, so epsilon x is, so u, v and w are the displacement in x, y and z direction. You all can hear and see the whiteboard, right?
Yes, ma'am.
Yeah, fine. Okay. So I don't know when we can again go back to classroom. This is really awful. Anyway, so epsilon x is del u by del y, sorry, del u by del x. Okay, and epsilon y is so sigma x is equal to 0. So epsilon x is equal to 0. So this goes to 0. Epsilon y is also equal to 0. Epsilon z is also equal to 0. Gamma xy is also equal to 0. So what I have is tau xz is equal to minus g theta y, and that is equal to del u by del z plus del w by del x, and tau yz is equal to g theta x, and that is equal to del v by del z plus del w by del y. Okay, so I know I have this relation. So we can solve this entire system, solve for u, v and w, assuming the boundary condition so we assume that if I have a shaft, this point A is constrained. There is 0. Okay, if we assume this boundary condition, then this is the solution for this set of equation is u is equal to minus theta z. I'm not solving it right now. So u is going to be minus theta z into y. V is going to be minus theta z into x, and w is going to be 0. Okay, this is the solution of this set of equations. Okay, these equations are pretty easy to solve, but it's a very lengthy process, so I'm not going into that. I mean, if anyone face any problem, you can let me know. Okay, you try to solve.
One doubt, ma'am.
Yeah.
Ma'am, in this third equation, tau xz is equal to del u by del z, that equation. Like tau is actually the shear force, shear stress.
Sorry.
How is it equated to?
Sorry.
Oh, okay.
Okay.
It's fine.
Okay, so I'm going to get this solution. So this is the displacement. Now, how are we going to solve this? So, see, I know mt. I know the applied torque mt. From mt, I can find out the rate of twist angle phi. From there, I can find out theta. Okay, if I know theta, I know the displacement in x, y, and z direction. Now we see that the w is equal to 0. This is equal to 0. This is out of plane deformation. Okay, And that shows that when I have torsion of a circular shaft, there is no out of plane deformation, okay, or no out of plane warping. So this is what it gives me. Okay, now U and V are of this form. Okay, so this shows that the circular shape. So if you take U square plus V square, it is always going to be theta Z into R. Okay, that shows it's always going to remain circular. Okay, and there will be no distortion of the circular cross section. So that's all with the torsion of circular shaft. Is there any question? I'm going to take a bit of pause and let me know if there is any question.
Ma'am, can you just repeat how is it maintaining circular cross section?
Okay, so see, U is, so if I take just square root of U is in x direction. Okay, if I take the resultant of U and V, these are in the locus of x and y are in the locus of a circle, right? So this U and V also have to be in the locus of the circle.
Okay, it's clear now.
Okay, okay, fine. So any question in torsion of circular shaft? Okay, just to summarize, therefore, the torsion of circular shaft is a problem where the circular cross-section remains circle. There is no out-of-plane deformation. Because of the applied torque, there is a pure shear, okay, tau R, which can be resolved into two components, tau xz and tau y. That's all. Fine. And we can see that this is a solution from the theorem of elasticity. So it's a pure elastic solution problem. Right? So this is the building block. Why I did this example, this is going to help you to understand how are we going to solve the torsion problem of a thin wall shaft, okay, which is a real aircraft structure. Right? So any questions here? No.
Ma'am, so you said that U and V have a circle. I mean, they're always in the circle because it's the equation of a circle. But what about the radius? Like,
so radius can change, right? That's what I think so. I mean,
yes, ma'am. Like according to this equation, like
if you have a constraint, if you have a constraint at A, if one end is fixed, then of course the radius can change.
Okay.
If it is not fixed, it's a rigid body kind of motion. It does just turns and doesn't change.
Yes, ma'am.
Okay. So if there is no more question, I will move into the next topic, which is torsion of non-circular shaft. Okay, so Coulomb gave this theory for circular shaft, which we have studied all this while. Okay, now what happens is that Navier's, famous from the Navier-Stokes theorem, okay, he adopted the Coulomb's theory and applied it for a non-circular shaft, any cross section, any arbitrary cross section. Okay, he applied the same theory to a non-circular shaft, and it was the solution that was obtained by applying Coulomb's theory to non-circular shaft was uh, not satisfying the experimental observation, was not in line with the experimental observation. Okay, so if it was seen experimentally that when we apply pure torque to a non-circular cross section, maybe a rectangular cross section, the out of plane deformation or the out of plane warping is not equal to zero. Okay, the out of plane, unlike circular shaft, there is an out of plane warping, and the shape of this out of plane deformation varies from cross section to cross section. Okay, so Saint-Venant, the same Saint-Venant who is famous for his boundary condition theorem, he gave a theory of torsion where he assumed the displacement function of this given form. The in-plane deformation, that is U and V, is same as that of the circular cross section, but the out of plane deformation is theta into some warping function psi x of y. Okay, this psi is going to vary with different cross section that we are considering. Again, so let me write down the highlights of the torsion of non-circular shaft. The non-circular shaft, it is again a pure shear problem. There is only pure shear stress produced. Okay. There is out of plane deformation. Okay. And but the out of plane deformation, you have to see that the out of plane deformation is just a function of x and y. That is the in-plane coordinate. So the out of plane deformation is same for all cross section. Okay. So out of plane deformation psi xz xy is same for all cross section. Okay. So these are the basic features of torsion of a non-circular shaft. Okay. Now we will see whether this solution is satisfying the equations of elasticity, and how are we going to find out the wrapping function psi, that is a function of x and y. So that is our next job in hand. Okay. So if there is no question, I will move on to the derivation. So let me reiterate, my next job is to see whether this satisfies the equations of elasticity and the boundary condition, and if it is doing so, how are we going to find out the wrapping function? So this wrapping function is still unknown to us. We need to find this out. Okay, so let me see what are the stresses. So if these are the stresses, then sigma x, you can find it out yourself. Sigma y, sigma z, tau xy is equal to 0. Okay. If you can derive for yourself and see that all these four stress components are 0. The only non-zero stresses are tau a tau xz. What is tau xz? Tau xz is del u by del z plus del w by del x. Okay, that is going to be del u by del z is minus theta y, and del w by del x is plus theta del psi by del x into g, okay, or g theta del psi by del x minus, and similarly tau yz is going to be g theta del psi by del y plus x. Okay, so these are the two non-zero stress components. Now let us see whether it is satisfying the equation of equilibrium. Okay, so now I have to apply this and this to the equation of equilibrium and see whether they are satisfying the equation of equilibrium. I'm not going into that elaborate process. You can do it for yourself, right? The three equation of equilibrium where you put this values of these stresses and you see whether they are going to get satisfied. The body forces are zero. Okay, we are not considering weight. Now, if you do so, you will see that the equations of equilibrium are satisfied if del 2 psi to 0. So if my wrapping function that condition that we can get hold of function which is satisfying this condition, then my equation of equilibrium are also satisfied. Okay, done. So first part is done. Now let us see the boundary. Let me see the whether they are satisfying the boundary condition.
Ma'am, can you repeat the last part? Your voice wasn't clear.
Ma'am,
Okay.
there was lag in the whiteboard also.
Okay. So what I was trying to say is that so only tau xz and tau yz are not equal to 0. All other stress components are 0. Okay. Now we have to see whether these are satisfying the equations of equilibrium. So if you put the values of the stresses on the equation of equilibrium, you will see that all the equations of equilibrium are satisfied provided under only with one condition, that del psi x square plus del 2 psi del y square is equal to 0. If this condition is satisfied, if wrapping function is satisfying this condition, then the equations of equilibrium are satisfied. Okay, so if I can get hold of a wrapping function which is satisfying this condition, then my solution is going to satisfy the equation. Is that okay?
Ma'am, can you tell us why this is the case? I mean, why if this is true, they're satisfied?
Why this condition is coming?
Yes, ma'am.
Okay, so let me write down the equations of equilibrium. Okay, x is anyhow equal to 0. Sigma x is 0. Tau xy is 0. Now what is tau xj? Tau xj is g theta del psi by del x minus y. Okay. Now see, psi is a function of x and y. Psi is a function of x and y. Okay. Del psi by del x is also a function of x, y. So when I take del tau xz by del z, this is going to be 0. And this is also going to be 0. So this entire thing is equal to 0. Okay. Is that fine?
Yes, ma'am.
Yeah, okay. So this equation is satisfied. So similarly, del tau xy by del x plus del sigma y by del y plus del tau yz by del z plus y. That is my second equation. Okay, let me see. Y is equal to 0. Sigma y is equal to 0. Tau xy is equal to 0. What is tau yz? Tau yz is g theta del psi by del y. Del psi by del y plus x. Okay. Now if I take this by z, this is a function of only x and y. That you have to keep in mind. Okay, so this goes to 0, this goes to 0. So this whole thing goes to 0. Okay, so the second equation is also satisfied. So let us now come to the third equation, which is del tau xz by del x plus del tau yz by del y plus del sigma z by del z plus z. Okay, z is anyhow equal to 0. Sigma z is equal to 0. So I am left with this. If I am left with this, let me see. What is this? Okay. So what is del sigma z by del x? Del sigma z by del x is g theta del 2 psi by del x square. That's all. And then plus g theta del 2 psi by del y square. And if that is equal to 0, which implies del 2 psi by del x square plus del 2 psi by del y square is equal to 0. Okay, so if the warping function is satisfied this condition, then it is satisfying all the equations of equilibrium. Is that okay?
Yes. Okay.
Yeah. Okay. Okay. So now we see that only if this is satisfied, my solution that I have, the one that Senvenan has given is satisfying the equation of equilibrium. Okay. Now let me see if it is satisfying the boundary condition. So let me just keep it written down. Equation of equilibrium is going to give me only this condition. Okay. Now let us see whether it is satisfying the boundary conditions on the lateral side. Okay, so let me write an arbitrary cross section. This is a pure arbitrary cross section. Okay. So so n is the normal to the boundary. Yeah.
Can you just repeat the last part? How did we get it to satisfy that d square psi by dx square plus d square psi by dy square equals 0?
Okay. So if we go to the last equilibrium equation, okay, in the
Yes.
last equation of equilibrium, let me just quickly write it down. So the last equilibrium equation is, okay, so in this z is equal to 0. Okay,
Yes.
sigma z is equal to 0. So only tau xz and tau yz are non-zero. So
Yes.
let me write down the expression of tau xz. So that is del x into g theta into del psi by del what? Del psi by del x minus y plus del y of g theta del psi by del y plus x. Okay.
Yes, ma'am. I got
So
it, ma'am.
that, oh, got it, right? Oh.
Yes, ma'am.
Okay. So now let me write down the boundary condition. So what is x hat? X hat is sigma x into L plus tau xy into m plus tau xz into n. So sigma x is equal to 0, tau xy equals to 0, n is equal to 0. Okay, so this is satisfied. So let me write as y hat. Y hat is tau xy L plus sigma y m plus tau y z n. N. Okay, so this is equal to 0, this is equal to 0, and n is equal to 0. Okay, so this is also satisfied. This is also equal to 0. No externally applied force. No externally applied force. Okay. Now, let me see the third boundary condition, which is z hat. Z hat is equal to tau x z into L plus tau yz into m plus sigma z into n. Okay. Now, this is anyhow, n is also equal to 0, z is also equal to 0. Z hat is also equal to 0. So what I'm left with, I am left with tau xz into L plus tau yz into m is equal to 0. If I see that this is being satisfied, then my boundary conditions on the lateral surface is satisfied. So let me just write it in detailed form. So I can write this as g theta del psi by del x minus y into L plus g theta del psi by del y plus x into m is equal to 0. Okay, so g theta is gone. So I have del y by del x minus y into L plus del psi by del y plus x into m is equal to 0. Okay, so this is what I get out of the boundary conditions. Okay, now I have to, so this is my equation 1 and this is my equation 2. Okay, equation 2, this is equation 1. Okay, so now in order to solve, in order to find out a real solution of the torsion of non-circular shaft, I have to get hold of a warping function which is going to satisfy equation 1 and which is also going to satisfy equation 2. You will be able to appreciate that it is rather easy to find out a warping function that is going to satisfy 1. Okay, that you can find out by trial and error. But for an arbitrary boundary condition, the boundary condition can be as arbitrary as you can think of. Okay? To find out the warping function which is going to satisfy this equation is going to be extremely difficult. Let me also write down L and M in terms of dy and ds. You can see that L, which is cos of nx, is nothing but dy by ds, right? And M, which is cos of ny, is nothing but dx by ds, minus of that, because I am going in the minus direction. Okay, so I can put the value of L and M here, and you see that you have to find out, it's a very difficult, it's almost impossible to find out a warping function which is going to satisfy the equation 2, which gives you the boundary condition. Forget about the boundary condition and the top and bottom surface. Even we are stuck at the boundary condition on the lateral surface. We cannot get hold easily. See, it's a doable problem, but it's a difficult problem. Okay, it's of course doable. You can always get hold of a warping function which is going to satisfy this condition as well as this condition. But it is a difficult problem. Okay. Now, our next job is to solve this difficult problem. Can you do some manipulation, some tricks, so that we can solve this problem? Okay. So with that, I will, in the next class, that is tomorrow, I will try to find out, okay, other alternate way, a trick rather, okay, to solve this problem so that we can solve the problem of a non-circular shaft. Okay, so that's all for today's class. So any questions? Anyone has a question?
Ma'am, about all that you've written during the class in these notes, will you be sharing any written form or slide or anything?
I will upload it in Moodle.
Okay.
Okay. And the recordings are also there. I will just edit those recordings and upload it.
Yes, ma'am.
So any other question? If it is nothing, then we will close the class. Thank you.
Thank you, ma'am.